Welcome to Massive Open online course on fluid flow operations. In this lecture, we will discuss about the fundamentals of flow. Here, how the flow will be flowing and what will be the mathematical expression for the flow, and how this mathematical expression can be actually represented. Generally, you will see that there are two methods. One is Lagrangian methods and another is Eulerian's method. We will be discussing here these two methods of this fundamental flow, and based on these two methods, some characteristic features of this flow will come here, like how whenever fluid is flowing through the pipe, and what will be the streamline of the flow, and what will be the stream function for that, how stream function is related to the streamline function, and also how the potential line of the fluid flow can be expressed. This will be discussed here. You know that this mathematical method to express this fluid flow, there are two methods. One is called the Lagrangian method, and in this case the movement of this particle is defined with respect to its location in space and time from a fixed position at a start of the motion. And in this case, generally Cartesian system, if we represent this mathematical expression for the fluid flow, the position of the fluid particles in space will be represented as a function of some space and time. So, in that case, if we say that at a particular position the particle is there, then you can express this position of the particle in terms of x. So, it will be equal to function of some location a b c and with respect to time t. Similarly, at a position y, then how this the position of the fluid particles in the y direction, then how it will be represented. Again, it will be a function of some location, some parameters, and then with respect to time. And in this case, what will be the velocity of that particular fluid particles there? Then it will be represented by u in the x direction, and it will be defined by dou x dou t, and v in the y direction it will be dou y dou t, and also in the z direction it will be dou z dou t. Similarly, the acceleration of the particle in the x direction and y direction, and also other direction like z direction, can be represented by this expression here a x and a y and a z here. This is the method to express this express the fluid flow as per this Lagrangian method. Similarly, Euler methods also one important description to express the fluid flow characteristics here. So, in this case it generally describes the overall flow characteristics at various points as fluid particles whenever it will be passed through, and in this case it gives the various quantities such as velocity, acceleration, pressure, density, etc. at any point in space and time from a purely mathematical viewpoint here. So, the velocities at any point x, y and z in x, y and z direction respectively can be written as like this. U will be is a function of here f1 x, y and z t, and v will be again function of this space and time. Similarly, for w in the z direction it will be represented by a function of here f x, y, z and t. And finally, the resultant velocity based on this x, y, z directional velocity will be represented by this v will be is equal to root over then u square plus v square plus w square, where u, v and w are the velocity components in x, y and z direction respectively. Now, whenever fluid is flowing through a particular direction, so you will see in a 5 there will be some particles that will be flowing in a particular path. So, that whenever particles will be moving in a particular path, what will be the line of that path, it will be called as path line. Similarly, if we joining those particles and it will be some line of that fluid particles, it will be sometime represented by this streamline. But this streamline is defined as the line where its tangent at its point on it indicates the direction of fluid at that point in a streamline. So, in that case you see here the video, one videos that here how this fluid particles in a particular line it will be flowing, and whenever it will pass through an object, it will get an obstruction and it will spread over the surface of this solid particles, and it will get the disturbance, and still it will be following at a certain streamline there. But at that particular location you will see there will be a breakage of that streamline. But beside these points you will see some other lines there will be following a certain fashion. So, certain path the particles will be followed. In that case the line in this case where its tangent the particle's tangent at its point on its will be indicating the direction of the fluid flow at that particular point, that will be called as streamline here. So, here it is shown in the picture, and also a streamline can be obtained by drawing a curve following the flow trace here shown in the video. And also here if we represent this trace by this blue line here, in this case suppose this is the streamline. So, at a particular point, what suppose this is in y direction, this is in x, this is in z direction, this is in z direction, this is in x direction. So, if there is a resultant velocity suppose in the v, then what will be the velocity component in the x and y direction, and from which you will be getting what should be the slope of this line there. So, a streamline can be obtained by drawing a curve here just by tracing the S point of tangent on the line. So, the velocity vector has no normal component in this case of streamline. There will be no flow which crosses this streamline also, and gradient of the streamline will be represented by du by dy or dy by dx here. So, if the velocity component in x, y and z direction are u, v and z respectively, then the equation for streamline can be expressed by this dx by u that will be equal to dy by v and will be equals to dz by w. So, main important point here that the velocity vector will not have any normal component, and there will be no flow which crosses this streamline. So, because that the direction of this fluid will be as per the tangent of the particle flowing at each point there. Also, the streamlines around a body vary according to the relative relationship between the observer and the body. If the body here, if the body will be moving here, this line, this is one body, the white face here. So, this will be one body, and around this body the fluid will be flowing, and the streamline of the fluid flow is represented by this curve here. In this case the movement will be relative to each other. So, in this case if moving of this solid particles is observed by the observer, then you will see the streamlines around a body that will vary this according to the relative relationship between the observer and the body. And by moving both a cylinder and a camera, suppose if you are observing by camera, if the camera is I think if it is moving with the observer and also observer and the cylinder also moving. So, parallelly if both are moving, and then there will be relative movement of both the observer and the cylinder. So, in that case by moving both a cylinder and a camera, if we placed in a water tank at the same time, it will be possible to observe the relative streamlines there. So, by moving just the cylinder, the absolute streamlines can be observed here. So, if it is suppose cylinder, it is moving at a certain directions and also streamline is also as per this flow. So, you will see there will be a relative movement, there will be relative relativity of that movement of the streamlines and the solid particles there. Now, we have discussed about that streamline, what will be the streamline function is there. So, and what will be the velocity component in the u, v and w direction, and based on this we can express the equation for streamline by this equation here. So, based on this equation, let us do an example here. In a two dimensional flow, if the components of the velocity are given by, suppose u is equal to a x here and v is equal to minus a y. So, find the type of streamlines and draw them here. So, very interesting that here it is given the velocity component u will be equal to a x and then d u by d x will be equal to what, a, and also v is equal to minus a y. So, d v by d y will be equal to minus a. Now, d u y by d x from these relationships we can express that it will be v by u. So, it will be minus y by x after substitution, and then you can express this d u by d y that will be equal to minus d x by d x. So, these things are coming from this first d y by d x is equal to minus y by x. So, and after this equation if you take the logarithm on both sides they are integrate on both sides, then you can get that ln y will be equal to minus ln x plus constant here. So, finally, you can say that ln x y will be equal to constant. So, this is the equation of the streamline. So, this ln x y that will be equal to constant will give you this type of streamline here. This is hyperbola type streamline. So, if your velocity component is following, suppose some u is equal to a x, suppose here u will be equal to 2 x or something, some straight line is formed, that is the equation or velocity is expressing by this, and v is equal to minus a y. Then from this equation and based on the equation of streamline, you can have this final form of streamline equation. So, based on this, what type of streamline equation you can easily calculate. Now, suppose this constant is coming any value, suppose if it is ln x y is equal to 2, then what should be the y value, that will be equal to, if suppose ln x y is equal to 2, then y will be equal to 2 by e to the power or exponent of 2 divided by x. So, if you change the x value, then respective y value what should be that, if you plot it, then you can get this type of hyperbola type of streamline. So, this is one example how to calculate the streamline. Now, what will be the stream function? Another important that if we consider a two dimensional steady incompressible flow, where A dashed and B dashed as shown in figure here are the streamline which will be representing the flow, then the flow per unit time that across the points A and B of the two streamlines here, then it will be called as a stream function. So, the flow per unit time across the points A and B, across the point A and B. Okay. So, it will be represented by a stream function that will be denoted by psi here. So, the line joining AB may be here, see this line joining AB may be APB or AQB, but the flow per unit time will remain same here. So, this is the main important point, that to express the stream function you will see that the flow per unit time across points A and B will remain same. It does not matter whether it will go this different way like APB or AQB, but the flow per unit time will remain same. So, based on this concept, if we consider that psi at point A is 0, then psi at point B will be flow per unit time, that is psi. Then the function psi, which will be a function of x, y and t, which will be defined by the amount of discharge across the coordinate as here dou psi, that will be equal to u into dou y, and that will implies that u will be equals to dou psi dou y. So, this will be discharged across dx. So, dou psi will be equal to minus v dou x, which will imply that v will be equals to minus dou psi dou x. So, dou psi by dou y, it will be, that is the discharge across dy, whereas dou psi dou x will be discharged across dx. So, this is basically the how much water will be flowing for unit time across the point A and B of two streamlines there. So, the discharge between two streamlines will be the difference in the values of the stream functions. So, based on this you can calculate what will be the stream, what will be the discharge per unit time based on this concept. Now, what will be the properties of stream function? Along a streamline, of course, it will be constant, and the rate of discharge of stream function with a distance in an arbitrary direction is proportional to the component of the velocity normal to that direction, and the velocity vectors may be found by differentiating the stream function here, and the algebraic sum of the stream function for two incompressible flow pattern is the stream function for the flow that will result from the superimposition of these patterns. So, here in this case dou psi 1 dou s plus dou psi 2 dou s, that will be equal to dou psi 1 plus psi 1 dou s here. So, this is very important that just this psi 1 and psi 2 are superimposition of these patterns here. So, whenever you are considering that streamline, of course, that should be that must be constant, and the rate of surge of stream function, rate of change of that stream function with respect to distance in any arbitrary direction, that will give you the change of rate of change of stream function based on the velocity normal to that direction. And the velocity vectors also can be found by differentiating this stream function. and of course, the summation of two stream function will be superimposition and just by summing up those based on a certain distance. The stream function of a flow, if it is given by the expression psi is equal to 2 x square minus y square as an example. So, in this case what should be the components of the velocity and the resultant velocity at a point, that will be denoted by x is equal to 2 and y is equal to 2. That means, at point 2 and 3 what should be the velocity component and the resultant velocity, if you know the stream function there. So, stream function is y is equal to 2 x square minus y square. Then if you differentiate it with respect to y at point 3, then you can get minus 2 y, that means minus 2 into y is equal to 3 here. So, it will be minus 6. Similarly, if you differentiate it, that dou psi dou x at point 2, it will be coming as 8, since it will be negative for velocity in the y direction, it will be represented by minus 8. And so, resultant velocity will be equal to here v will be equal to root over u square plus v square. So, this will be coming as 10. So, what will be the resultant velocity if the stream function will be 2 x square minus y square at any point, then you can easily calculate by this stream function. And also another example, like if there will be an uniform indefinite flow parallel to x axis, and also if flow parallel to y axis, if it is inclined stream, then what should be the stream function. So, if is there uniform indefinite flow parallel to x axis, that means if u is equal to u 0 and then v will be equals to 0, therefore, we can say minus dou psi dou x, that will be equals to 0. Hence, psi will be equals to a function of y only, or u will be equal to dou psi dou y, that will be equal to u 0, from which after integration you can calculate what would be the psi. So, psi will be equal to here u 0 into y plus constant. Similarly, flow parallel to y axis, it will be psi 1 will be equals to v 0 x plus constant. And to get the stream function for an inclined stream, the above mentions are of course superimposed like this here. So, it will be psi 2 will be equals to psi, this one in the here psi, and then plus psi 1, this is psi 1, then stream function for an inclined stream, it will be equal to u 0 y minus v 0 x. Now, another important characteristics of the fluid flow, that it is represented by the stream tube and the stream filament. Here, what is stream tube? Stream tube is nothing but the bundle of streamlines from inside of a general flow, which is called stream tube, as shown in the figure here. Here just bundle of the stream function, streamline, bundle of the streamline here, that will make this stream tube, and here. So, in this case, why the stream tube should be required to know? This is very useful in analyzing flows, basically for just considering a certain what is that control volume to analyze the fluid flow. The streamlines drawn through each point of a closed curve, that will constitute a stream tube. So, this is basically one control volume, you can say. So, stream filament is also one other important that means characteristics to represent the fluid flow. In this case, the stream filament is nothing but a stream tube whose cross section is a curve of infinitesimal dimensions. So, in this case, this cross section should be very small. So, if you consider that cross section is very small or as a point here, you will say that you can represent the fluid flow in a refined manner. Another important one is called streak line. In this case, you will see the figure here. If we suppose allow some dye in a fluid flow, you will see how the dyes particles will be following a path, dyes particles will following a path here in the flow. So, the path that given by this or produced or generated by the fluid particles, or here in this case by dye particles, it will be called as a streak line here. The line formed by a series of fluid particles, in this case which pass a certain point here in the stream one after another. So, this is the definition of the streak line. So, it will be a line that will be formed by a series of fluid particles, and of course, it will pass through a certain point in the stream one after another. And also that instantaneously, if you cast the lines by injecting dye into the flow through the tip of a thin tube, the streak lines can be easily observed. So, how here see this is one the streak line, see here, if we represent this, this is one path line and this is one path line. The this is a simple, these particles will follow this point with respect to time, and here these particles will follow this time here this position. So, the joining of this position changing is called the path line here. This is also another path line by this particle, this is also another path line by these particles. Now, at a certain point in a stream, you will see in this case, if we consider that only these particles will, whenever at a certain point it will follow, then this particle by taking a camera or by snapshot, you will see at that particular location these particles will be there on their particular path line. So, if we joining this if we join these lines, then you can get what should be the streak line of these fluid particles there. And path line is nothing but the trace of one particle starting from one particular point in the stream, and by recording one movie or video film, a balloon released in the air, you can observe that the path line of that particular balloon that is released in the air. And also another important line that represent the fluid flow characteristics, that is generated by drawing a line through adjacent particles in the flow at any instant of time. So, this is the here you can say this path line, the particles will follow at a different time interval or at a different time where these particles will be there at the particular locations there, and timeline is there that here drawing, if you draw the line through the adjacent particles in flow at any instant of time, then you can say this will be your timeline there. Now, in the case of steady flow, remember that the streamline, path line and streak lines all will be same. Another important characteristic is called potential line. The line of equal velocity potential are known as potential lines. They are orthogonal to the streamlines. So, this potential line will be the orthogonal to the streamlines. In fluid dynamics, you will see the potential flow that will describes the velocity field as the gradient of a scalar function, which will be called as a velocity potential. That is characterized by the irrotational velocity field, and these are applied for the outer flow description of the field for aerofoils, water waves and osmotic flow, and also you can say groundwater flow. Also, potential flow theory cannot be applied for viscous internal flows. So, potential flow, that limitation is that you cannot apply this potential flow theory for the viscous internal flows. Now, how actually one can represent this velocity potential mathematically? If we consider a flow that takes place in a pipeline with a pressure difference, then in that case the direction of flow that will take place from higher to the lower pressure. So, this is basically the potential difference. Now, thus the velocity of the flow in a certain direction generally depend upon the potential difference. So, then it will be represented by the velocity potential and denoted by a phi here. So, dou phi will be equal to u into dou x. So, from which you can say that what will be the u, then it will be dou phi dou x. Similarly, in the y direction v will be represented by dou phi dou y. So, phi is the velocity potential and v is the velocity, and how then it will be related. So, how velocity at a particular direction, how it will be related to the velocity potential, you can easily express by this. U will be equals to dou phi dou x and v will be equals to dou phi dou y, and also w will be equal to dou phi dou z in x, y and z directions respectively. So, based on these functions you can define the velocity potential, and also how the velocity at a particular directions can be obtained from this velocity potential you can also have. Now, what should be the relation between velocity potential and stream function? Stream function we know that psi, whereas this velocity potential velocity potential is phi. So, what will be the relation between phi and psi? So, if we consider that u in the x directional velocity u, so in that case as per velocity potential this will be dou psi dou phi dou x, and as per that stream function it will be dou psi dou y, and in the y direction velocity will be equal to dou phi that will be equal to minus dou psi dou x. And so, these equations are called actually Cauchy-Riemann equation, and this is represented by the what is that the velocity potential and stream function relationship, and this has given by Cauchy-Riemann, and from this equation you will be able to calculate once you know the psi and phi and what should be the velocity there, and also if you know the velocity what should be the psi and phi also you can get it. Now, if we represent that, if we get this d phi will be equal to dou psi dou x into dx plus dou psi dou y into dy, and along the potential line there will be no, I think what is that velocity potential, then d phi will be equals to 0. So, based on this you can express what should be the what should be the velocity, what should be the I think tangent of that velocity potential line, that it will be dy dx, that will be equal to minus u by v. So, and also if we express that d psi will be equals to dou psi dou x into dx plus dou psi dou y into dy, and along the streamline then d psi will be equals to 0, based on which what will be the tangent for in the y and x, like the dy by dx will be equals to v by u. So, thus in this case, so we can get the slope of this stream function or streamline and the potential line. So, for the potential line, the slope will be equal to dy by dx, that will be the minus u by v, whereas for streamline the slope will be equal to v by u. So, if we relate with that, then you can say that slope of potential line will be equal to negative of inverse of slope of streamline. Let us do an example here. Suppose a stream function is given by the expression psi, that will be equals to 3 x square minus 3 y square. Then what should be the velocity potential function based on this stream function? So, we know that u will be equal to dou psi dou y. If we differentiate it, we can get minus 6 y. Similarly, v will be equal to minus dou psi dou x as per definition, then it will be equal to minus 6 x. So, dou phi dou x as per definition of the velocity potential line. So, it will be is equal to u, which is nothing but minus of 6 y, from which if you integrate it, then you can get phi will be equals to minus 6 x y plus some constant, which will be a function of y. Again, dou phi dou y in the y direction, and that will be equal to v as per definition. Then v is equal to what? V is nothing but dou psi dou x negative of this, then it will be minus 6 x, then from which after integration you can calculate what will be the phi here. So, phi will be equal to minus 6 x y plus again constant, that will be a function of x. So, from this equation 1 and 2, you can easily say that this phi will be equal to minus 6 x y plus some constant c here, c is the constant. So, you can easily calculate what should be the potential line based on the stream function. Now, another important you can graphical important characteristics of the fluid flow, which will be represented graphically. So, it is called flow net. This flow net, it is a graphical representation of streamlines and perpendicular equipotential lines. Here see the diagram, here see this as per what is that arrow, that these lines are, if we consider that streamlines, then it will be the orthogonal to this streamline will be here, it will be as potential line here. So, potential line and streamline will be perpendicular to each other. The condition of the orthogonality of the streamlines and the potential line is that dou phi dou x into dou psi dou x plus dou phi dou y into dou psi dou y, that will be equal to 0. So, this condition should be fulfilled, then only you can get this type of flow net there. So, where actually this flow net is being used, or why it is so important? It is important to analyze the flow problem in which boundary configuration and flow conditions are such that the mathematical analysis is very difficult. Like Francis turbine runner, in that case you will see flow through this runner, there will be a complex flow pattern. So, to represent this flow pattern, the flow net will be to be used to characterize this flow. Now, another important things that what we have to know, that how different types of or how these fluid particles will be displaced. Now, different types of displacement of the fluid particles occur whenever fluid is flowing through a particular conduit, like translation, like rotation, like distortion or deformation. What is that translation? As per figure here, see here, this element here moves, this element moves bodily in some direction. Here suppose A is moving to CD, CD is moving to C dashed, D dashed, AB is moving to A dashed, B dashed, like this. So, flow through pipes of a constant diameter. In this case, pure translation does not change any stress in the element. So, translation means here the fluid particles will be displaced from one location to the another location here. So, without having any stress there. So, that is ideal translation. Whereas, rotation is the pure rotation, it is called in that case when there will be a no cause of any stress. That means, there is no relative motion with respect to the rotating system. So, in this case you will see if we consider this rotation here, the fluid particle just is pivoting from one point to in a certain direction here, it is just rotating this here. So, important that here there will be also no cause of this stress here for this ideal rotation. There is no relative motion with respect to the rotating system here. So, it will be just from this just simple just moving just pivoting at a particular point. Distortion or deformation, in this case stresses of course will be produced on it, and in this case two types of distortion we can get. One is angular, which is represented by maybe theta, how much theta angle is I think that is made based on the stresses. Now, if we consider here see angular deformation here, just simply just pressing out or by stressing on this 2 point in this direction, you will see there will be a deformation of this object or fluid particles there with an angle theta 1 and theta 2. Now, theta 1 is counterclockwise angular distortion, and theta 2 is called the clockwise angular distortion. Whereas, linear distortion in this case here volume of course will be changed totally, it will be stressed in such a way that the volume will be changed there. Like if you increase the temperature, the volume of the gases will be increases. Now, general types of fluid flow, we will discuss what are the different types of fluid flow can represent that. One is like steady state and unsteady state. If it is flow is with respect to time, then it will be unsteady state. If the flow does not change with time, then it will be steady state. Uniform and non-uniform, sometimes the flow will be uniform and non-uniform, sometimes the velocity of the fluid or streamlines will be changing on its different location. Also developed flow or undeveloped flow. Sometimes the flow will be initially it will be disturbing, and after a certain time the flow will be getting uniform flow throughout the cross section of the fluid. And so also you will see cross section of the pipe. Also you will see that the average velocity will be same, average velocity of the same in each location of the pipe. And compressible or incompressible flow, viscous or inviscid flows, there will be some laminar or turbulent flow, 1 or 2 3 dimensional flow, rotational, irrotational, supercritical and superficial and subcritical and also subsonic, sonic and supersonic. These are the various types of fluid flow. We will be discussing one by one what is that. Let us see other what is the important auxiliary definitions to develop the equation of a fluid flow. Like you have to know the discharge, that is volume per mass of fluid that is flowing for unit time across any section of a conduit which is known as discharge or rate of flow. Before analyzing the equation of fluid flow, you have to define a system. Sometimes you have to consider a portion of the fluid that specially identified for an analysis. and also you have to consider a control volume. It is a real or imaginary volume which can be defined in a problem or the purpose of easily identifying the system. Also cross section, it is an imaginary surface through which this fluid will be flowing. So, that also should be defined in your case of analysis of fluid flow. Now, consider the steady and unsteady flow. The steady, what is that steady flow? A flow whose flow state expressed by the velocity, pressure, density or other variables at any position that will not change with respect to time. So, you can express this steady flow as suppose this P dP by dt will be equals to 0. That means, pressure does not change with time. Also dV by dt will be equals to 0. What does it mean? Here there will be no change of velocity with respect to time. Unsteady flow, it is defined as the flow whose flow state will change with respect to time. So, that will be called an unsteady flow. So, in this case you will see that dP by dt not will be equals to 0, there will be certain value there at a certain rate that pressure will change with respect to time, and also the velocity with respect to time will change. So, that will be called acceleration. So, in that case it will be unsteady flow. What is that uniform and non-uniform flow? How it will be defined? The fluid or flow parameters at any given instant that will remains same at every point in the space. It is called then uniform flow. That means, here dou v dou s at time t, that will be equals to 0. That means, at any position if you go in the 5, when 5 you will see there will be no change of velocity. So, it is called uniform flow. Non-uniform flow on the other hand, if the fluid or flow parameters at any given instant will change with distance in the flow. So, that means, dou v dou s at t 0, that will not be 0, that will have some value. So, that the velocity will be a function of distance there. Like here in this case, this is uniform flow, at any point here their velocity will be same. So, that is why it is called uniform flow, whereas you will see if the velocity pattern like this here. So, you will see the velocity at any point it will be changed with respect to distance or any location, then it will be called as non-uniform flow. What is developed flow? In this case, you can get the velocity profiles, we will observe, we will discuss later also. The velocity profiles, whenever fluid is flowing at a certain velocity, it will change with respect to I think axial position and time. So, if suppose this velocity profile do not change with respect to downstream any coordinates like x, y, z, then you can say it will be developed flow. The momentum also does not change in the flow direction in this case. So, the pressure in the flow direction will balance the shear stress near the wall. So, this type of condition will be represented by the developed flow. So, when the velocity profiles does not change with respect to any coordinates in the downstream, that is in the direction of this flow, then you can say it will be a developed flow. The developed flow may be unsteady, that is it may depend on time, such as when a valve is being opened or closed. In that case, you will see there will be a velocity will be change or may not change, that based on the operating condition. If it is not changing, then it will be developed flow at unsteady condition. Now, what is the viscous and inviscid flows? Viscous flows, that case all fluids that have viscosity, and if the viscous effects cannot be neglected during the flow and also representation of the flow, then it will be considered as a viscous flow. Whereas, the effects of viscosity can be completely neglected with no significant effects on the solution to a problem involving the flow. So, in that case it will be called as inviscid flow. Inviscid flows are easier to solve than viscous flows. Viscous flows, some extent it is complicated to represent here. So, in this case you see here as per diagram, a viscous flow within boundary layer here, whereas inviscid flow beyond this subject surface, some away of this object, there will be a no viscosity effect. So, that will inviscid flow, whereas adjacent to this solid surface the flow will be get disturbance and there will be some change of this velocity pattern here. So, due to this it will be represented as a viscous flow within the boundary layer. Now, next one is very important, that whenever you are going to represent any velocity pattern or acceleration or density change, pressure change of the fluid flow, you have to consider it whether it is in one dimensional or in two dimensional or three dimensional flow. If you are considering that three dimensional flow, suppose a ball whenever it will be flying in the air and a flow around a moving automobile, that will have velocity components in x, y and z directions. So, it will be called as three dimensional flow, and the flow velocity will be represented by this spatial coordinates like u, x, y, z and the time. And for two dimensional flow, in this case the liquid running between the two parallel plates cross cut velocity to the plates and parallel to the flow. So, in that case two dimensional flow, like it will be only x and y direction and with respect to time, only two velocity will be considered here u and v. Whereas, one dimensional flow, in the suppose narrow tube, the fluid is flowing through that narrow tube, you will see the flow will be in one dimension. Two dimension there will be no variation of the velocity or acceleration. So, it will be called as one dimensional flow. So, liquid flowing in a tube in terms of average velocity, then the flow has a velocity component in one direction only. So, it will be called as one dimensional flow and it will be represented by u will be equals to u x t. So, u, the velocity of the liquid will be represented only the spatial coordinate x and time. What are the laminar and turbulent flow? In this case you will see one important criteria to consider whether this fluid will be laminar or turbulent, whether it will be very streamlined, very slow in motion the fluid flow, or the fluid particles will be moving haphazardly by just changing its location with respect to time. Now, if you consider that there will be a flow, fluid particles will be moving in a certain fashion that the fluid particles will follow a straight line path. So, in that case it will be a laminar flow, whereas, if the fluid particles will not follow that straight line, that means here at any position it will change its what is that straight line path, then it will be called as turbulent flow. Here if we consider that by this diagram, just see this diagram, that if we inject some dye, the dye will be represented by this yellow color. You will see at a certain time if we inject it, whenever it will be flowing through this flow stream, you will see the solid particles or that is dye particles will be moving haphazardly like this. So, this will be what is that turbulent flow. And whenever liquid flow in a certain fashion, that the dye particles will follow some extent linear, sometimes very just small change of its location with respect to liquid flow, then it will be either considering laminar or turbulent. So, it will be called as transitional flow. And if that dye particles just follow the straight line, there will be no the zigzag path of the moving of these particles in this liquid flow. there will be no change of its location from its one direction. So, then it will be called as laminar flow. Okay. Like here. So, one important criteria to represent this laminar or turbulent flow or transition flow, it is called that Reynolds number. What is that Reynolds number? The Reynolds number is a dimensionless group or number, which will be defined as that the ratio of two forces, that is called inertia force and the viscous force. The ratio of inertia force to the viscous force, it will be called as Reynolds number. Like here, the mathematical representation of this Reynolds number is rho u d by mu. What is rho? Rho is the density of the liquid, u is the velocity at which the liquid is flowing through the pipe, d is the diameter of the pipe. So, in this case, and the viscosity is the viscosity is represented by mu. So, rho u d by mu, if we see that the what should be the dimension of this Reynolds number, it will not have any dimensions here. So, in this case rho u d by mu, you will see what will be the dimensions here, it will be dimensionless. So, in this case, if this Reynolds number, suppose liquid is flowing with a certain velocity u, the density of the liquid rho, diameter of this pipe is given to you, and you know the viscosity of the fluid, and if after calculation about then what should be the Reynolds number? If Reynolds number is coming greater than 4000, then you can say it will be turbulent flow. Of course, it is applicable only for pipe flow. For other channel flow, this Reynolds number may change and other things that will be discussed later on. So, in this case for pipe flow, if Reynolds number is greater than 4000, then you can say it will be turbulent flow. It is totally unpredictable, rapid mixing will be happening inside the tube or pipe. And if this Reynolds number within the range of 2300 to 4000, then you can say this will be a transitional flow, either laminar or turbulent, there will be a mixed there. So, you cannot consider that purely it will be laminar, you cannot consider the purely turbulent. So, it will be transitional. So, like turbulent outburst is one type of example there. Like and also here, if Reynolds number, if it is less than 2300, then you can say it will be laminar flow. It is very obvious, then you can see easily, and also it will be predictable and slow mixing will be there. So, this is the flow, different types of flow, and so we can have that different type of flow, whether it will be the steady state, unsteady state, uniform, non-uniform, viscous or non-viscous, or it is laminar or turbulent. So, before going to study all other that means flow characteristics of the fluid, you have to know all these things. Whenever you are going to represent the fluid flow operations, whether that operations is in a laminar condition or turbulent condition, whether it is in whenever there will be a reaction is going on, suppose if the what will be the flow pattern, whether it is the laminar or turbulent. If you are supplying, if you are suppose if you are controlling the temperature, whether by laminar flow or turbulent flow, if you are considering any chemical engineering operation or mechanical engineering operation, heat transfer device, there also you have to design all those things, you have to consider that whether this laminar flow or turbulent flow, or that inviscid flow or non-inviscid flow, even some other steady or unsteady state there. For further calculation you have to do. To know the velocity profile also you have to consider whether laminar or turbulent flow, all these things you have to calculate there. So, before going to details of the fluid flow operations for mathematical representation of velocity profile or one dimensional flow, two dimensional flow, even some other device design. So, you have to know these flow characteristics, that is fundamentals of the fluid flow there. So, for further reading you please follow this introduction to fluid mechanics by McDonald, Fox and also other suitable fluid mechanics, any book you can follow there. Mainly I can suggest that even Bird, Stewart and Lightfoot is one important book, very nice books for getting the velocity profile, nature, all these things they are discussed. And also the McCabe Smith also you can follow for the definition of the different types of fluid flow. So, thank you for this attention.